Welcome to the deep dive. Today we're wading into one of the most critical challenges in modern oncology, triple-negative breast cancer, or TNBC.
It's a really formidable opponent.
Absolutely. And for you, our listener, who needs to know what the cutting edge of TNBC research really looks like, we have a fascinating stack of sources today detailing a potential game changer.
And it's so needed. TNBC gets its name because the tumor cells, they lack the three most common receptors, estrogen, progesterone, and HER2.
Which means the standard targeted therapies just don't work.
They don't. And despite, advancements in chemotherapy and even some immunotherapies, we're still facing these high recurrence rates, aggressive metastasis. There's just a desperate lack of targeted treatments.
That context is so crucial. It really underscores why finding these new, unique vulnerabilities is so important. So let's zoom in on the specific target of this deep dive.
Okay.
We are focusing on a protein called secreted frizzled-related protein 2, or SFRP2 for short.
Right. And SFRP2 isn't just a passenger in this disease, it's an accelerator. What immediately jumps out from the research is just the sheer volume of it.
What do you mean by volume?
In invasive breast cancer tissues, SFRP2 can be overexpressed, well, dramatically. We're talking up to a nearly 20-fold increase compared to healthy tissue.
Wow, 20-fold.
Yeah. That kind of amplification, it signals that it's doing something fundamentally important for the cancer survival.
So if it's elevated that much, what exactly is its role? Is it a key regulator or something?
It's like a master switch for tumor promotion. It helps the cancer thrive in multiple ways. Crucially, it activates the cellular superhighway, the FZD5-NFAT pathway.
And that's essential for angiogenesis.
Exactly, building new blood vessels to feed the tumor. But beyond that, it helps cancer cells migrate, which encourages metastasis, and it actively puts the brakes on programmed cell death, or apoptosis.
So it's doing everything the cancer wants.
Everything. When you see high SFRP2 levels, you are seeing an independent predictor of a poor prognosis. It's a bad sign, full stop.
So when you identify a protein that is doing that much damage, the logical step is to try and block it. And that brings us to our mission for today.
Right.
We're dissecting the mechanism of an experimental therapy, a humanized monoclonal antibody, the HSFRP2 mAb, that's designed to do just that. We're going to explore how this antibody not only delivers a direct hit to the tumor, but, maybe more profoundly, seems to recruit and reprogram the body's own immune system.
Okay, let's start with the basics, the fundamental proof of concept. When this antibody was tested in mouse models, specifically with that really challenging MDA and P231 human TNBC line, what did the sources reveal about its efficacy?
The results were substantial
Wow.
and sustained. Treatment with this HSFRP2 antibody resulted in a massive reduction in the primary tumor size.
Oh, massive.
Compared to the controls, we saw a sustained 61% reduction in tumor volume. And that's over the course of treatment, which lasted more than 10 weeks.
So this isn't just slowing growth.
No, this is delivering a decisive, sustained blow to the primary tumor mass. And when you're talking about treating something for, 78 days, the safety profile becomes absolutely paramount. How did the mice tolerate this kind of aggressive blockade?
They tolerated it really well, and that's a critical point for any future clinical application. Throughout the entire 11 weeks of treatment, the mice showed no signs of significant systemic toxicity.
So no weight loss, lethargy, that kind of thing.
None of it. No weight loss, no hair loss, no lethargy. It's an early indication, of course,
Yeah.
but it suggests the antibody is highly selective for its target. That promises a potentially high therapeutic index for patients down the line.
That's a great initial signal. But with TNBC, the biggest fear is always metastasis. Does this antibody just hit the primary tumor, or is it effective against the cells that have already broken away?
It proved to be highly effective against metastasis as well. Across multiple models designed to mimic metastatic disease, the antibody significantly cut down the formation of lung metastases. The sources confirmed really robust statistical significance in reducing the number of these secondary tumors. So it seems to be interfering with the entire metastatic cascade. So if the antibody is blocking SFRP2, and you said SFRP2 inhibits cell death, the natural conclusion is that the treatment is promoting apoptosis in those runaway cells. Is that what they saw?
Precisely. They saw a striking increase in programmed cell death right inside the metastatic tissue in the lungs. In one model, the number of apoptotic cells more than doubled in the treated group compared to the control.
So the antibody is basically pulling the tumor cell's own emergency brake.
Exactly. It's forcing those malignant cells into self-destruction.
You also mentioned earlier that SFRP2 promotes angiogenesis, giving the tumor its own little delivery service for nutrients. Is the antibody starring the tumor as well?
Yes, and that anti-angiogenic action is a key part of the mechanism. The sources show the treatment actively reduces the presence of a marker called HIF-1 alpha.
Okay, HIF-1 alpha. For our listener, how should we understand that? Think of it as the tumor's SOS signal. When a tumor grows too fast, it runs out of oxygen, it becomes hypoxic. HIF-1 alpha is the protein the tumor ramps up to panic build new blood vessels.
So the SFRP2 antibody treatment actually lowered that signal.
It did. It decreased the amount of this SOS signal in the primary tumor by almost 15%. This provides some real mechanistic proof that by blocking SFRP2, the treatment is throttling the cancer's ability to build new infrastructure. It's cutting off its supply lines.
So it's acting like a dual agent, causing internal self-destruction while also cutting off the supply chain. But here's where the narrative takes a major turn, right? The immune component.
This is the novel insight. This is what elevates this work beyond just a simple receptor blockade.
So when the research team analyzed human TNBC tissue, they made a critical discovery about where SFRP2 was actually located.
Exactly. They found SFRP2 wasn't just expressed by the cancer cells themselves, which, you would expect. It was deeply integrated into the entire tumor microenvironment, the TME.
And where specifically?
They found it heavily co-localized with the immune cells. Nearly all of the tumor-associated macrophages, or TAMs, were positive for SFRP2. Same with the tumor-infiltrating lymphocytes, the TILs.
Okay, so the protein is literally coating the tumor's immediate immune defense.
Right, which suggests the antibody could be a tool for immune modulation, not just direct tumor killing.
That opens up a whole new line of thinking. It means the antibody isn't just targeting the cancer, it's targeting the cops that the cancer has bribed to look the other way.
That's a perfect analogy. We need to talk about those TAMs, the tumor-associated macrophages. They're generally split into two types.
M1 and M2?
Right. M1 macrophages are the first responders. They're anti-tumor, pro-inflammatory. They actively kill cancer cells. Then you have M2 macrophages, which are the tumor's best friend.
They're the bribed cops?
They are. They're immunosuppressive, they promote tissue repair, angiogenesis, and they protect the cancer. In progressive cancer, M2 dominance is really common.
So the therapeutic goal is to flip that switch, to increase the M1 to M2 ratio. Did the antibody do that? Did it reprogram the macrophages?
In the metastatic sites of the treated mice, absolutely. The HSFRP2 MAB treatment substantially boosted the M1 to M2 ratio. In one model, the ratio jumped from just about 1-to-1 to significantly higher.
So it's shifting the immune environment from one that protects the tumor to one that attacks it.
The environment became far more anti-tumorigenic, yeah.
That shift must be driven by a specific chemical signal. What's the immunological currency that the antibody is using to make this M1-M2 switch happen?
The key player is Interferon-gamma, IFN-gamma. Researchers treated macrophages outside the body with the antibody, and they saw a massive biological response.
What kind of
A
response?
significant multifold increase in both the genetic instructions, the mRNA, and the corresponding protein production of IFN-gamma.
I see. And IFN-gamma is the primary instruction manual the immune system uses to switch a macrophage into that aggressive anti-tumor M1 state.
It's effectively unleashing a powerful, localized immune booster. And the effects just cascade downstream.
How so?
They validated this by looking at T cells. When T cells were exposed to these newly activated antibody-treated macrophages, the T cells showed a significant spike in activation and proliferation markers.
So the reprogrammed macrophage is now better at activating the T cells to go fight the cancer.
Much better. And this was confirmed in the animals as well. The serum IFN-gamma levels were significantly increased in the treated tumor-bearing mice.
So we have this clear, powerful chain of immunological events. Blocking SFRP2 on macrophages forces them to make IFN-gamma, which then recruits and activates T cells, tilting the whole microenvironment toward attack. But does this hold true for humans?
That is the essential question for clinical translation. So the research team turned to data from the Cancer Genome Atlas, the TCGA. They looked at over 1,000 human breast cancer patients, and they found a profound and highly significant inverse correlation. The more SFRP2 a human tumor expressed, the less immune-activating IFN-gamma it had present.
That is the ultimate validation. It confirms that SFRP2 is a central immunosuppressive mechanism in human disease.
Exactly. It means blocking it is very likely to have this IFN-gamma-mediated immune-boosting effect in patients, just as it did in the lab. It transforms our understanding of SFRP2 from just a simple growth factor into a powerful immune regulator that's actively helping the tumor hide.
So by targeting SFRP2, we are effectively disabling the tumor's immune cloaking device.
That's it.
That brings us to the third major implication here, which tackles the sheer practical reality of treating TNBC resistance. Chemotherapy resistance, especially to frontline drugs like doxorubicin, is one of the biggest drivers of recurrence.
It's the wall we constantly hit. So the researchers actively modeled this problem. They developed a doxorubicin-resistant TNBC cell line.
A line that was totally unaffected by the chemo.
Completely. Even at very high concentrations, that would typically kill a sensitive cell line.
So the big question, did the HSFRP2 antibody still work against those chemotherapy-impervious cells?
Remarkably, yes. The HSFRP2 AB treatment was still able to induce cell death, apoptosis, in the doxorubicin-resistant cells, and with high statistical significance.
That's a crucial finding.
It is. It suggests the antibody acts via a pathway that's fundamentally different from doxorubicin. It could offer a new therapeutic door for patients whose standard chemo regimens have failed.
So that provides hope for chemo-resistant disease. But what about immunotherapy resistance? The sources note a close relationship between SFRP2 and another protein, CD38.
Right, and CD38 has been linked to resistance against checkpoint inhibitors.
So what's the significance of that connection?
Well, the connection is incredibly tight. SFRP2 and CD38 show very high co-localization, nearly 99% across all the key players in the tumor microenvironment, the cancer cells, the TAMs, the TILs.
Which makes SFRP2 an attractive indirect target. But walk us through why targeting SFRP2 is actually preferable to targeting CD38 directly.
Okay, so if you target CD38 directly, you might get an anti-tumor effect. But CD38 is also present on healthy, normal immune cells, hematopoietic cells.
So you get side effects.
Serious side effects. Directly blocking it systemically can lead to things like neutropenia, compromising the patient's overall health.
It's like using a sledgehammer when you need a scalpel.
Precisely. The key here is specificity. SFRP2, crucially, is not found on those normal, healthy hematopoietic cells. So by targeting SFRP2, the antibody selectively reduces levels of the co-localized CD38 only in the tumor microenvironment.
So only on the macrophages and lymphocytes surrounding the tumor.
Yes, without causing those severe systemic side effects. It's a very elegant strategy to enhance the immune response locally and improve the therapeutic index.
We've spent a lot of time on the low toxicity profile. Let's finish by just confirming the antibody specificity in the body. Did they confirm that it actually homes in on the tumor as intended?
They did, using biodistribution studies. The HSFRP2 antibody showed what's called selective accumulation. It strongly preferred the tumor tissues compared to a standard control antibody.
And what about other organs?
Well, the levels of the antibody were found to be significantly lower in critical non-target organs, like the heart, the lungs, and skeletal muscle. This validates that the antibody is indeed traveling where it needs to go, maximizing its punch against the cancer while leaving healthy tissue largely untouched.
So to bring this deep dive to a close, we've really witnessed the emergence of a multi-pronged attack against triple-negative breast cancer. This HSFRP2 monoclonal antibody, it successfully inhibits growth and metastatic spread by cutting off blood supply and boosting apoptosis, and it also overcomes that stubborn hurdle of chemotherapy resistance.
But the truly novel takeaway here is the immune reprogramming. By targeting SFRP2, this antibody doesn't just block a signaling molecule. It acts as an immunological conductor. It flips the macrophage ratio toward that anti-tumor M1 phenotype and unleashes a cascade of IFN-gamma, the body's natural cancer fighter.
It fundamentally rewires the microenvironment for attack.
That's it, exactly.
So what does this all mean for the future? Well, our focus today was TNBC. SFRP2 is an elevated protein that drives disease in a variety of other aggressive cancers: osteosarcoma, angiosarcoma, pancreatic cancer. So here's a final thought for you to consider. What might the success of this targeted immune-modulating approach mean for the broader landscape of oncology? If blocking SFRP2 can turn the immune system against TNBC, what other cancers might be susceptible to having their immunosuppressive shields dropped by a similar strategy? Something to think about as we look at how we fight cancer tomorrow.